For the last section of electromagnetic induction, we need to look at the reasons for power losses in transmission lines and real transformers. What I'm going to focus on is transmission lines. So, we start off with the energy being produced in the power plant. Once you get the current and the voltage which is supplied by this, it is sent to a step-up transformer which steps it up from 12,000 volts to 240,000 volts here. So 12,000 volts, 240,000 volts. So we multiply by 20. So there's a step-up transformer of a factor of 20, which also means that the number of coils on the secondary coil will be 20 times as much as the number of coils in the primary coil. So we have 240,000 volts in the high voltage transmission line, but you cannot put 240,000 volts into a house. So then it has to be stepped down again to a step down transformer, and then step down again to a house. And we're going to look at an example of why that is soon. With the use of transformers, electrical power is sent across long transmission lines at high voltages. So it must be sent at high voltages. Why is that? Now, if the voltage is high, it means that the current must be quite low. So there will be less power loss in the lines. So the energy that is lost by the electricity going through the lines depends on the current. Depends on what the current is. The higher the current, the more this wire will heat up and the more energy you will lose. So the use of high voltage step up and step down transformers. Let's look at an example here with some made up numbers. You have a 2 ohm power line. So in other words, the resistance of the line is 2 ohms between a house and the power station. The house needs 240 volts and the power station provides 240 volts, and let's say it needs 100 amps. 100 amps is rather large for a house, for an example. So here's the house. Here's a power station. What is the total power supplied? We know that the power is equal to current times by voltage times by potential difference. So P is equal to IV, 100 times by 240 gives us 24,000 watts is provided to the house. Okay, it's rather large for a house, but just to work it as an example. So 24,000 watts is transferred to this house through this single line. We have to calculate the power loss in the 2-ohm distribution line. Remember that the power loss is equal to I squared R. I is equal to 100, square it, times by R, which is 2, gives us a value of 20,000 watts. It means that of the 24,000 watts that the power station is supplying, 20,000 watts are lost in heating up the cable as the current passes from the power station to the house. This is not good. So we use a transformer which is used to step up the voltage by a factor of 10. So the voltage goes up by 10, which means that the current comes down by a factor of 10. So the current, which was 100 amps, is stepped down by a factor of 10 to 10 amps. Now we can work out what the power loss is in the new system. So this is the power station, this is the house. This time we have a step-up transformer here, the transformer is inside here, and a step-down transformer here. Let's find the power loss in the distribution line. Now we know that it's I squared R. Now I is not 100 anymore, it's now 10. And R is still the resistance of the wire. So it's going to be I squared, which is 10 squared, times by 2, which gives us 200 watts. Now this is much better. The power station is able to supply 24,000 watts to the house, and only 200 watts are going to be lost in heating up the wires, because it's a small current. If it were a large current, then a huge amount would be used up in heating the wires. Notice that this is 20,000 watts, and this is 200 watts. This is a factor of 100 different. Why is it that the power loss is a factor of 100 different? Basically because it's due to the power is equal to I squared. The factor of the current was 10. I squared is 10 squared is equal to 100. That's why there's a factor of 100 in terms of the power loss. Okay, to end with, we have this war of the currents. 130 years ago, there was a debate between Tesla, who was keen on AC, and Edison, who was keen on DC. What was the best way of producing power? The war of the currents. Tesla believed that energy should be transferred with AC, Edison with DC. Now, basically, Tesla won because with an AC, a transformer can be used to change the voltage, and we've just found out that you need a very small current. The only way you can step up the voltage and step down the current, in other words, is to use a transformer, and transformer will only work if the current is changing. So a DC voltage cannot be transformed to a high voltage because it's not changing. That's the basis of electromagnetic induction, is that there has to be a changing current to produce a changing magnetic field. Otherwise, if you had DC, as the current was passing through the cable, you would get massive power losses. How could Edison overcome that? Wait a second. If you built a power station every mile, then the power losses would be very small because the cables would be very short. So that would be a solution, but it's not a very practical one. So Tesla won because with an AC transformer, it can be used to change the voltage. DC can't be transformed to a high voltage, which would be necessary to reduce the power or the heat loss in the distribution lines. Now, this is one aspect that we need to look at. Suggest how extra low frequency electromagnetic fields, such as those created by electrical appliances and power lines, induce currents within the body. Well, since all our devices work on AC, this changing current will produce a changing magnetic field, and that will induce small currents, eddy currents, in your body. Discuss some of the possible risks involved in living and working near high voltage power lines. Now, it has been suggested that the proximity to high voltage lines may cause leukemia in children. There is evidence that suggests that it probably is likely. There's a very small increase in leukemia cases near to high voltage lines. Also, I've heard it said that those who live near to high voltage lines can run a greater risk of suffering from depression. So, on that jolly note, we'll finish this topic, I think.